we can start.
All right, so welcome everyone to the third day of the GIAN course. So today we will learn about NV centers and magnetic sensors, part 1. This will be in the morning session, there will be lectures, and in the afternoon at 2 p.m. there will be a demo of the NV fluorescence in our lab. So we will all go there, and there will be a small demo, and I'll show you the experiment, basic experiment session. And in the evening, of course, we will have the
Good, thank you. Hello, everyone. So, like yesterday, I put the slide on this link, so you can download them. If take you a little bit of time for doing that, if you want. Okay. Good. So basically, we try to do I try to cover NV sensing for regarding the application to magnetometry, and we will do it in two parts. The first one is the CW regime, where we have a lot of applications already. We just continuously drive the NV center, monitor the spin resonance, and measure the influence of the magnetic field on the OD using the ODMR. And then we will see that you can do more advanced experiments and reach higher sensitivity if you do it in a pulse regime. And this is something I'm going to cover tomorrow, I hope, or maybe Friday, depending on what we do tomorrow, to prepare also the demo we will have. Okay, so this is the purpose of the talk today, and that will be, I guess, 1 hour long, and then we're gonna. I will switch to some illustration on this concept of NV magnetometry in this regime, regarding what we are doing now in the lab, in our lab, which is using this technique to probe magnetic and superconducting properties of materials at high pressure. So that would be more like a seminar-like presentation where I will describe our ongoing work on this topic and explain why we believe it's important to investigate these systems and why NV are really appropriate for doing these measurements. Okay, as you know, Yes, I asked yesterday a question. If we look to the G2 of a single center, NV center, we have this dome shape experiment, and there is different points that I would like to comment. The first one is that here, there is a kind of limit, and as soon as you measure something, if G2 is below 0.5, 1/2, you can say there is a single emitter. And the reason for that is the fact that for n emitters, then G2 at time tau equals 0 is 1 minus 1 over n. Okay, so if n equals 2, then I have 1/2. So it's a kind of basic threshold, okay? And that's the point. That tells us somehow, if I measure that here, I am at a level of 0.2 perhaps, let's say. So I'm clearly below that, and I can definitely say we have a single emitter. Now there is always some background in the experiment, so somehow the question when you do those kind of measurements is, do you take or not into account the background? Do you correct it or not? That's a kind of discussion that people can have. But what's also important is these features. And these features now we have it corresponds to a G2 value at that observed for this time scale, which is larger than unity. What does it mean physically? It means that actually, you have a bunched a bunching effect of the photons that are produced. And this is due to the shelving of the metastable state. If we look to the shelving of the metastable state, we have here our two-level system that pumping rate R, a decay time by spontaneous emission gamma, but at the same time, the system can leak to the singlet state. I only put one level, but this is a doublet, as we've seen. And in this shelving state, during that, we do not see emission at this wavelength. Okay? So if you look now to the emission, you will have, from time to time, the photons that are emitted like that are anti-bunch. Anti-bunch means that if I have a photon detected, I need to wait a given time that I get another photons. And the time, if I'm in the low excitation regime, is simply 1 over the decay rate, okay, the spontaneous emission time. So those photons are separated in time, grossly, by a delay of the radiative lifetime of the emitter. Okay? But now, as soon as the system goes to the shelving state, then the emission here is stopped. And now, if I look to another time scale, and it's actually what I'm doing by doing this G2 measurement as a function of the integration time, then I see bunches of photons. The first bunches of photons here, and then another bunch of photons. And this is what produced this effect of the G2. And you can do a calculation about that and that was a way that was used at the very beginning to quantify those leakage rate, which were completely unknown. So people do use the G2 measurement to understand somehow as an insight of the photophysics of the NV centers, and that has been quite important for the following, and also to understand all this leakage. Okay, maybe now I should perhaps discuss this. Wait, yes? Yes. Or just because at the beginning people didn't know that there were two systems. But basically, all this it's somehow the two levels that are here. It was just the model. But, so you can have different models and use them to have that. It's different possibilities. What you also need to perhaps I should mention that all these rates are not accurately known. They somehow, there's a large uncertainty about all these processes. And still people are just trying to investigate them. But it might depend also on the materials, on different properties. So the rates are known, but up to a given value, I would say, up to a given uncertainty. So as it was said, we have to do some evaluation of the course. So what we discussed with Professor Singh is that we would ask you to present a research paper. So you team up by four people, a team of 4 of you, and then you work together and try to understand one of those papers, and then you get something like 10 minutes of presentation, and we will have 2 to 3 minutes to discuss the paper with you. Okay, and then we do it with 8 teams. That means 8 papers. So I tried to select some paper that would somehow be complementary to what we discuss in the course. There are different things. Things that are more related to materials, papers that are more related to fundamental physics. So I will just describe them very quickly. The first paper here is a paper by Wartop, team by Jörg Wartop, where basically they demonstrated that you can enhance the coherence time, the T2 time of the NV centers, by removing the nuclear carbon, the carbon atom that have a nuclear spin, meaning the carbon 13. So you do a growth of diamond by CVD technique, where you have only carbon 12. and carbon-12 is nuclear-free, has no nuclear spin, and they demonstrated that there is a strong enhancement of the T2 time in this technique. This paper is from Misha Lukin team in Harvard, and basically they demonstrated that they could use NV centers as tiny thermometers, perhaps the tiniest thermometer in the world, basically, and the nanodiamonds were integrated in living cells, and they could measure the temperature inside the living cells using those nanodiamonds, and the NV centers here. Here it's another, here it's from us. So it's a paper I already mentioned, but that could be a way also to come back to the GSD and all that and try to understand the system. So how we can use a FIB machine to produce NV center. This is a paper again from Wartrup team, where basically they took a diamond slab and implanted N2 molecules. And the implantation of N2 molecules can lead to very close nitrogen atoms. And if you now convert them efficiently into two NV centers, those two NV centers will be so close that there is a magnetic dipolar interaction between them. And they observed this magnetic interaction, how it changed the spectrum. And at the same time, they could use address one and drive the other one through a kind of CNOT gate. So you have one qubit, which is one NV centers, acting on the other qubit, which is the other nitrogen NV centers. Unfortunately, it's a very nice scheme, but it cannot be scalable. Up to now, no one has really been able to establish it as a scalable system. But nevertheless, I think it's quite interesting to discuss and to know this work. This is by us. So it's what we called, it would be an illustration of what we call wide field NV magnetometry. And I will just give you a few slides and you will see how it works. And then there is a lot of discussions about that and why it was perhaps important to have those microdots. They were designed actually by colleagues at the Institut Curie in Paris. We want them somehow to be integrated into anvil cell. And after you want to be able to move these micromagnets inside the cell using an inhomogeneous magnetic field. This is also by us, where basically what we've been investigating. It's, I always mention that the NV centers is along the axis of the NV centers. Now, what happens if there is a magnetic field as a strong transverse component? Actually, that transverse component will mix up the quantum state, and that has some drastic consequence on the ODMR signal and the measurement stability. But you can use them in a way to have a microwave-free detection. And this paper is from our colleague from Thales. So this is a very clever idea about using the NV centers in an homogeneous magnetic field to have as a real-time spectrum analyzer. And for many applications, namely for radar, what you want to have is a complex signal, radio frequency signal that arrives, and you want to analyze it. But if you have the standard way to analyze a radio frequency signal, usually you will mix it with a local oscillator and do the measurement, and you sweep the local oscillator. That's the standard way we do spectral analysis. And that's a very different technique. Basically, you want to have a snapshot in real time of the spectrum. And you will see how this can be done with the NV center in the paper. And this is something a little bit different. Again, it's from us. So I'm sorry I put a lot of paper by us, but just not by, there are many other people that have done that, but just because I know them also. So, so it will be also easier to discuss with you and maybe also to help you during the preparation stage. We said with Kamal that we will have the Friday morning free, and you can work, and I can come and discuss with you to help you to prepare the system, your presentation. And this is how you can use the T1 time of the NV centers to measure, for instance, the occurrence, the coupling to gadolinium ions, and quenching parametric species that will, and this has been, there have been a lot of applications in biology on following these ideas of what's called relaxometry. So how you come quickly to thermal equilibrium as a T1 measured by the T1 time, depending on the environment. And you can use this measurement to somehow get information about the environment. That's the idea. So I hope this will give somehow a kind of, there's a lot of things that are now being done, and so many teams are working with NV centers at the moment worldwide. But somehow this will perhaps give you an idea, an overall view of the different developments that are ongoing at the moment. There are other things for sure. I do not want to be exhaustive, and that would be too long and perhaps not so interesting also after each topic by itself. Okay? So now perhaps on the NV, we come back to NV magnetometry, and also how we can use somehow the NV as spin qubit. So as I mentioned, you can do a very simple experiment on NV center, on single NV center. You have here a sample. On the sample, all these spots correspond to single NV centers. And then you have to put the microwave drive. And the microwave drive, there's a lot of possibilities to do it. One very simple one is just you simply put a wire, a copper wire, on top of your on your sample, and you drive through this wire the microwave signal. And the microwave signal will have an orientation that can induce the precession of the NV spin and produce a magnetic resonance. Of course, this is quite simple. What you can do is then lithography, deposit a metal and some antenna if you want. So there's a lot of work also about engineering the microwave field for doing that. But somehow for a demo experiment, this is far enough. So you just take that. You can have a microwave synthesizer, and for many experiments, you want to control the time during which you apply the microwave to produce pi pulse or pi over 2 pulse. So this is done by simple components like mini-circuit switch that you can use between the synthesizer and what we call the antenna that produce the microwave field. And now, for instance, what you can do is claim or add an external coil or a permanent magnet that will produce a small DC magnetic field that will change, that will split the level of the NV centers. And the NV centers is detected as previously. Green laser is used, focused on the beam to excite the NV centers. Then we raster scan the sample to find those, the NV center dispersed in the diamond. And the light that is emitted by the NV centers are collected by the same microscope objective. Then there is what we call the dichroic mirror. This dichroic mirror filters the light that is emitted by the NV centers from the green laser excitation, because as we know, there's a Stokes shift that corresponds to the luminescence of the NV centers. Then you focus it on a pinhole here, and the pinhole ensures a confocal detection. That means that you reject the light coming from most of the diamond sample apart from a few microns around the sample, the NV center, the focusing point of the microscope objective, and then you do a detection. That can be a G2 detector, G2 measurement, and then you have a beam splitter and two avalanche photodiodes that operate in photo counting regime, or you have simply one, and you register the number of count for a given integration time so that you monitor in real time, you monitor the intensity that is emitted by the NV center, and then you simply measure the intensity level as a function, for instance, of the microwave frequency. Okay? So doing that, it's a very simple system that you can build, and maybe we'll see that, or I will show this afternoon, and I will show you also by video what is in our lab. But it's not so difficult to do. Then we apply a field of 20 Gauss, for instance, that will create the splitting of the NV centers, and now we can address, for instance, one of the transition from 0 to ms equal -1 or 0 to ms equal ±1 by scanning the frequency and being on resonance of those well-separated system. And now I have a qubit. I can see that as a qubit, a two-level system associated to the spin 1 that I can manipulate using the microwave and detect using the light emission. Okay, so now all the process I'm going to describe are based on the combination of microwave drive plus the time window where I will do the detection of the luminescence, because all the detection has to come from the luminescence of the NV center. So one very simple experiment is to show, for instance, how we can have a spin state readout. So let's do the following thing. Let's start with the laser here. The first laser pulse that is here, I will try to follow it. That's the first laser pulse, 1. This first laser pulse, will polarize the system into ms equals 0. So I apply a pulse with enough power and long enough so that the system is now within, and a few microseconds is enough for that, the system is now pumped into ms equals 0. Okay? And now I just do nothing. What happens? And I will come back to the thermal equilibrium, because now the system is in the dark. Okay? So I will populate initially the system from to the ms equals 0 state, which has the highest luminescence level, I remind you, and then I wait. And then what I will do is that I have now a second pulse, which will be laser pulse that I will use as for the readout. So then I will measure the intensity emitted during this short laser pulse, and as short as possible, but long enough so that I have enough photons to know, to discriminate, to have a relevant information for the intensity level relative to shot noise. Okay? And what do I see? It's this first curve, this curve. So what I see that first the system goes up. And why does it goes up? Because, of course, I am in the 0 state. The 0 state is bright, very bright, so I have the high intensity level. And what happens then is the fact that the system will leak again. We have to be on this system, so this will be ms equals 0. That will be ms equals 0 on the other side, but that will leak a little bit to the ms equal. That won't stay for long enough in the ms equals 0. There will be some decay, but this it doesn't matter. I will repump them, but with that will be. So when there is this leakage here, then the system will progressively, or at the same time, I'm sorry about that. I should mention that here. The system will, in that case, also somehow it's in the dark. So it will there will be again a new population coming to ms plus minus 1. Okay, there is interaction with the system so that somehow you come back also to the ms equal -1 system. So what you see is a decrease of the intensity, okay? And the decrease of the intensity occurs within a few, typically within a microsecond. Now, at the same time, what I can do is something a little bit different. Or independently, what I can do now is that the second experiment. In the second experiment, I have here the laser, again the readout as previously, but now in between I apply a pi pulse. The pi pulse transfer the population to ms equals 0, to ms equal -1, okay? And since I'm in ms equal -1, I have this is the blue curve that I have here. I have a very weak signal coming from that. Okay, I have less intensity coming from the ms equal -1 signal, and this difference is simply the measurement of the different leakage. And then what I will do is that the system will go to the metastable state. Once it's in the metastable state, it cannot emit photons anymore. And after that, then it will, again, the metastable state will leak toward the ground state. And then, at the end, again, I come back to the thermal equilibrium, where the population is now at the same level on ms equals 0 and ms plus -1. And somehow, the contrast that of my ODMR measurement is this window, everything which is integrated here. Everything that is integrated in this window is proportional, will give me the ODMR contrast. So that experiment tells me that somehow, I have a kind of preferential, if I now look to, I can do it, I can do a kind of curve where somehow, as a function, if I do a CW experiment, what is the good? What is what will be the optimal value of the contrast? The optimal value of the contrast will be all that integrated in time. Okay, but I can do also a time window where I will measure somehow the contrast for if I want to have an accurate detection. And the time window that somehow, if I change the time of measurement for the spin determination, and will be as a function of the contrast between the two things, I will have something like that. Okay? And somehow this is something where this, at the beginning you have no information, that increases, then there's a kind of optimum, and after a while, of course, if you integrate too long, but you mostly see the thermal equilibrium and it comes back to 0. So somehow in this very simple experiment, you have a lot of things to understand regarding the mechanism of the polarization process. And it's another way also to understand or to measure the different leakage rate. And this is adapted from that paper and from an IISER thesis. Okay, now somehow this tells me how I can do. So one thing I will do now is to measure the Rabi oscillation of the system. So I remind you that the Rabi oscillation is the coherent drive of the spin. Okay? So I start by a laser pulse here of 2 microseconds long. This is my first pulse here. Basically, this is just intended to polarize the signal. Okay? So here, after that, I know that I am in the state, the spin state is in the ms equals 0 state. Okay? Then I wait, typically 1 microsecond. Now, I will apply the microwave pulse resonant with the transition between the two states, maybe ms equals 0 and ms equals -1, as I said previously. Then I don't know where I will end, depending on the length of the duration of that microwave pulse. I can do a pi over 2 pulse, I can do a pi pulse, I can do a 3 pi over 2, 2 pi, etc., etc. But then I do the measurement again, that's not a projective measurement. I will have to repeat it many times to have enough photons to have a reliable experiment at the end, a reliable measurement at the end. But then I reapply the same pulse. So somehow that's the new pulse acts as the first one. It's a kind of, it reinitializes the system. But I can now use a well-defined probe, so time window within this pulse, that will be my readout, as I explained previously. So now I can say with that, the number, the population difference somehow, this signal will tell me, would give me a signal that is proportional to the difference of population between the two states that I address by the microwave. Okay? So that will be here, 1 and 2. And that, or maybe 1 here and 2 here. And then that will be the population difference. And this readout by the intensity of luminescence is somehow proportional to this information, to this difference of population. And of course, and then I wait, and at the end of the green laser pulse, I'm again in MS equals 0 state, so I can then take that into account, use this now as the reference intensity level, and what I have at the end, by just comparing the two signals, I have measured the population rho 11 minus rho 22 divided by rho 11. Okay? Then that would be equal to unity in my case. Okay, that's at the reference. You follow me? It's okay? So I do that, and then using that, you see that appears the Rabi oscillation, depending on the time t that is used for applying the microwave. So I can really see in real time on a single electronic spin the Rabi oscillations that is induced by the microwave field. Now, if I wait, I've reproduced that for a long time, what do I observe? Depending on the microwave field, of course, as we have seen in the first lecture, the Rabi oscillation has a frequency that depends on the strength of the B1 field, if I use my notation of the first lecture, the driving microwave field, magnetic microwave field. So that I can control. It's simply the microwave power that I send in the antenna, basically. And depending on the microwave power that I send, I can choose either a weak magnetic power, and then I will see long oscillations, small with a small Rabi frequency. And now I can also increase the microwave power, and then now fast Rabi oscillation, the Rabi frequency has been increased by the microwave power. But at the same time, both signals, as you see here, decay, and they decay on what is the time scale of the decay, comparing to the parameter that we've seen. We have three possibilities, T1, T2 star, T2. What you would say? Sorry? T2 star, exactly. So the decay here, it's at T2 star. But you may ask yourself, it is strange, I'm working on a single spin. I told you before, the T2 star was in a standard NMR experiment, was associated to an ensemble. And this ensemble, being in an inhomogeneous magnetic field, with slight difference of the magnetic field, will somehow precess at different frequency, and then there is the scrambling of the signal, of the overall signal, that is due to that. Now I have a single spin. Can you explain me why I can nevertheless speak of T2 star in that case? Usually T2 stars in NMR is defined for an ensemble. Here I have that, but I do agree it's not the T2, it's the T2 star. And basically it's what you see. The T2 is going up to 2 microseconds in this experiment, the value, the decay time. And this is more a T2 star experiment. And the point is that if I have a single spin, T2 star, it somehow it can be associated to a jitter of the line. So somehow there is it's a process that will somehow my spin resonance, the spin resonance of a single NV can nevertheless wobble a little bit. So you can imagine like a laser. In a laser, we have two. If I speak about the line width of a laser, I have two types of line widths in a laser. The first one is called the shallow tones limit. It's a fact, it's linked, it's fundamental limit where you have a kind of, it's associated to the spontaneous emission, okay? And it's a little bit the same. We have here a fundamental limit that will be set by the T2. The T2 is, for instance, the nuclear spin nearby that will control the magnetic, that will induce some noise on the magnetic field and modify the spin precession. But you also, in a laser, it's very hard to be at the shallow tones limit. Usually, you have a cavity, and the cavity can have some fluctuations. So what you see in practice for a laser, it's this image of a narrow line that jitters. Okay, and of course, if you now integrate that in time, the actual line width will be the jitter convoluted by the natural line width. And at the same time here, in our we can see our NV centers as a narrow line associated to the T2, which a width of proportional to 1 over T2, and at the same time some jitter, and the T2 star is a convolution of all those processes, okay? And the jitter, we will see how we can control it. The jitter somehow can be controlled by some echo process, a little bit like before. So this is the I can also measure the T2 star time by exactly the same way, but perhaps more accurately, in the following process, in exactly what I mentioned before. It's a free induction decay experiment. But then what we do is what we call Ramsey fringes. And Ramsey fringes is we start by initializing the system in MS equals 0. We apply a first pi over 2 pulse. The pi over 2 pulse put the system in a coherent superposition of the two states, okay, MS equals 0 and MS plus minus 1, let's say. And then we wait. If everything goes well, this coherent precession will now precess around my magnetic field, and I can measure I can reapply after that a pi over 2 pulse. So if nothing happens, no decoherence process happens, then I have a pi over 2 pulse, a pi over 2 pulse. That's somehow equivalent to a pi pulse. So then I will have transferred the population from 0 to 1. Not exactly, because there is a time difference. So somehow if I take into a time difference, I will be able to get some modulation of the population. We will do the calculation tomorrow about that. So I see some fringes, and the fringes will decay on a time scale of T2 star. Okay, because of course, if there is any jitter of the line of the NV center, this will scramble the influence of the second T2 pi over 2 pulse compared to the first pi over 2 pulse.
Why did you apply a second pi over 2 pulse?
I applied the second pi over 2 pulse because I want to check if it's still coherent regarding the application of the first pulse. And somehow that would be equivalent to a pi pulse. Not exactly, because there is a phase that has appeared in between. So it's, then I would see some modulation of the population. But the amplitude of the modulation that are here will decay, and it will decay within the T2 star time since then the second pulse see a state that has been strongly modified regarding the coherent evolution. When I look at time, we will do the equations tomorrow. We'll try to do it. But first, I want just you to understand them by hand. So now we can look to these specific time, which are very important because somehow they will give me the line width of the spin resonance. The spin resonance, if I take that, for instance, I do a Fourier transform, and that will be the line width of my resonance. Okay? Now we will see tomorrow how we can use this scheme of Ramsey fringes to measure a magnetic field that is applied within that time. And we'll see that this is not possible. This will simply be a phase shift of the system, of the Ramsey fringe. Okay, so once I'm here, I can start with HPHT sample. So if you remind, this is the yellow sample that I showed at the very beginning yesterday. The nitrogen content is around 100 ppm. Carbon-13 is a natural abundancy, 1%, but this is somehow negligible. What matters is the nuclear spin, the electronic spin bath of the nitrogen impurity. Those nitrogen impurities have a spin, electronic spin 1/2, and it's this bath that will control somehow the T2 times. And the T2 times will be much shorter than 1 microsecond. So for instance, if I take nanodiamonds, the T2 star will be a few hundreds of nanoseconds for NV centers embedded in that. So to increase the T2 star, what you go is to remove the nitrogen impurities as much as possible as you can. So you work with a nitrogen content that is part per billion, and you can show that now the T2 star is limited by the carbon-13, the nuclear spin of the carbon-13. And that's around 1%. And that corresponds to a rule, an experimental rule that tells you that the NV concentration times the T2 star is about 3 microseconds times part per million. So if I have now an NV sample like that has a concentration of about 1 ppm, 2 to 3 ppm, the T2 star will be around a few microseconds. Okay? And we will see that tomorrow also in the demo experiment. Now what I can do, and this is one of the papers that I propose in the list, is to reduce the carbon-13 abundancy, and then we go from this to this. So now it's a sample that is grown only with carbon-12. So we take methane, so it's a plasma, in which instead of injecting methane with the natural abundancy in carbon, you have produce methane only with carbon-12, and that people know how to do that. It has been purified. And then with that, now you can significantly reduce by 2 orders of magnitude the number of carbon, and then you significantly increase the T2 star to about 100 microseconds. And somehow all the NV practical magnetometers are now built from those materials in which you will have a concentration of NV, which will be of a few ppm within this carbon-12 environment. Okay? And that sample that becomes now expensive because, of course, you need this special isotope selection somehow in the methane gas that you will use, and this is quite expensive. So it's not, so then you have to discuss whether you need that or that, because the cost of the sample will be significantly different, and that's of course important for going to industrial applications. Okay, now I want just to give a small hint about the NV magnetometry. What matters somehow in all our experiments is the width of those peaks. Okay, and the signal to noise associated to the width of those peaks. And that somehow depends on different factors. So we made a few years ago a model for this CW magnetic sensing on a single spin, and it has been adapted for ensembles by Ron Walworth and his team in Harvard, where basically I tried to explain a little bit the model. So I think it's rather, it took us some time to do that. So basically, that's also in the thesis of Anaïs Dréau and in this paper. So basically, and it was done with Vincent Jacques, we applied, you have different rates. You have population rate, and population rate, that means that you transfer the population to the different states. And there are also the leakage. And at the same time, you have the coherent drive by the microwave on the spin here. And in the experiment, we just use a magnetic field to address only two transitions. It's simpler. So somehow you have different things. You have different parameters. You have parameters that are intrinsic to the diamond. For the population, it's the spin relative relaxation, T1 or gamma 1, which is in the millisecond range. At the same time, we have what is a coherence. So somehow, if you build a dipole here, a magnetic dipole oscillating, how long it will survive due to the magnetic environment. And then basically what matters is the dephasing gamma, but also gamma 2 star, okay? Or the inverse, this is 1 over T2 star. Okay, and this taking into account the value that we have before would be of the order of 2·10⁵ per second. And then you have also the rate, because each time that you have some pumping here, optical pumping effect, of course, you erase the magnetic dipole. You transfer to the excited state, so the coherent, so the dipole has been completely erased. So for that, we have, it depends on the pumping efficiency, so simply the intensity of the laser here divided by the saturation intensity on this electronic transition. And so we have different rates. The rate for the population is how fast we polarize in the system, and we have also to take into account the influence of the singlet manifold or the leakage to the singlet manifold, where the system will survive during a time of about 200 nanoseconds. And there is also the influence of spontaneous emission that will bring the system back here. And as soon as you bring back here, you can reestablish the coherence of the magnetic, you will have the magnetic drive. So there is a competition between all these processes. The pumping process that are somehow a reset of all coherent magnetic interaction, and at the same time, the magnetic interaction that will be used to produce a microwave resonance and somehow the peak of the ODMR signal. So if you do that, then you write out some block equations. So it's standard equations adapted from the formalism, for instance, of a two-level atom interacting with the driving field. But you add now the non-coherent process that you have to take into account that would somehow erase either the population or the coherence of the magnetic interaction, the dipole, the magnetic dipole. And at the end, using that, you can find a compromise between the different, the influence of the laser and the microwave power and magnetic field, and demonstrate that typically the sensitivity in this DC scheme, where you simultaneously apply the microwave and the laser, is around the microtesla by already optimizing the best. So getting a few microtesla, it's somehow the good, what you can reach with those kind of system. Okay, on a single NV. Now you can increase it a little bit if you have now more NV centers, because of course the sensitivity will go as square root of the number of your emitters, because then you have more photons to detect. So, but that's the kind of system that we can have. So if we want to have higher sensitivity, so for instance, targeting the picotesla and even below, we need other schemes. And we need really to enhance that. Then we will apply a pulse scheme to avoid at least this kind of competition between the pumping by the laser and at the same time the coherent drive of the magnetic dipole. Okay? So but the DC scheme can be very important for many applications already. One of the first one that was developed, proposed and developed, the first realization was done in Jörg Wartrup team, was to attach a nanodiamond at the apex of a tip and use that to monitor the stray magnetic field produced by a sample here. And using that, you can really now, by scanning the nanodiamond, you can really map the stray magnetic field with an accuracy which is remarkable, that can be below a few, that can reach a few nanometers. What is also important is that you measure the field that is average on a volume which is typically the size of the NV center, and the size of the NV centers is nanometer. So you average the sample over this volume, and again, an important feature is the fact that this nanodiamond is non-magnetic. Otherwise, you would see the response of the nanodiamond. But since diamond is non-magnetic, you only see the NV center that is inside. And also that works in ambient condition, and the magnetic, so you compete somehow with another technology that was developed to measure, to map magnetic field at nanoscale, which is called magnetic force microscopy. So this is a magnetic cantilever, and due to the interaction of this magnetic cantilever and the magnetization of the sample, you have a bending effect, and you measure this bending, and you could map the system like that. The magnetization like that. But in this case, you have a strong back action because your tip is magnetic, strongly magnetic. And somehow there is a lot of bias and parasitic effect associated to the magnetic properties of the tip. Here we have a tip that is non-magnetic, no back action on the system. And this is described in length in this review paper. Just the sample that was, the system that was built in the team, what was here was a thesis of Loïc Rondin, where we have now the sample is here, and of course most of the magnetic sample are non-transparent. They are metallic or a garnet or whatever. So you do not see through them. So what we did was to have a system in which we could polarize the NV centers and detect at the same time, which was not the configuration that was used in the first demonstration. Nevertheless, what we have here is scanners. So we can scan the sample on XYZ with this piezo stage that you see here. It's piezo stage from this company, Atocube. So we designed the system somehow with them. And there are 3 other scanning stages that are used for positioning the AFM tip. And the tip you don't see, but was somewhere here. And you have a nanodiamond that was grafted at close to the apex of the tip. And then the distance was about 1 millimeter, about approximately, which was enough, nevertheless a little bit challenging, to position the AFM tip in between the sample and the microscope objective. And this is a kind of image of the tip. So it was a very specific tip that had that shape so that we could really plunge toward the system and have this configuration. So what we see is that the resolving power is you want to measure, to have a resolution as close as possible to the nanometer range. But what matters is what set the limit of the resolving power. Suppose that I have 2, I want to, the resolution I will have on the mapping of the magnetic field will be 5 to 100 of nanometers, and this is simply due to the height of the nanodiamond with respect to the apex of the tip. And it's very hard to put the nanodiamond really, really at the apex. There's when you glue it or you attach it just by forces, spontaneous forces, basically the nanodiamond will remove, so will go up. And at the very beginning, we tried to somehow use very tiny nanodiamond. It was quite difficult. But then we realized that due to this effect, we could work with larger nanodiamond, and somehow that would produce the same effect. But they were larger, easier to attach, and the strength was also stronger. The bonding strength was stronger. And the sensitivity is limited by, of course, the coherence time of the NV spin, but also the photon collection efficiency. And what has been remarkable is that people have been able to produce diamond tips. So you start from a diamond crystal, and then you shape using lithography technique and etching technique. You shape really tip from that. That can be attached now to scanners. And what you have here, it's you see here the diamond here, and on here there is the diamond tip that has been really shaped, curved into on the diamond sample, and on the apex of the tip there is an NV center. And that's really remarkable technological achievement, but that led also to a much more practical system and with more control, because now, for instance, you know the orientation of the NV. You can now even purchase tips that are grown, that are realized from 111 material. So, for instance, the NV is perpendicular to that, and that will be very sensitive to a stray field along this direction, for instance. Or you can purchase P tips that are in 100 direction, and the NV will be like that. So very sensitive now to in-plane magnetization. So you can really choose a lot of configuration of the tips that are available. They are very expensive also. A tip of 111 material will cost around 4,000 euros, and you can imagine how easy they are to break. So, okay, it's a good business somehow. And there's two companies, another one in China also, but two European companies that now sold these NV scanning magnetic microscope, Cunami in Basel and Cusabre in Zurich. Both are Swiss companies with different approach. Yes?
How many NV centers are in the...
So you do it with only one NV centers. So now there have been tips that are produced with 2 NV with the idea of trying to implement gradiometry. Because sometimes it's very interesting to have the gradient of the magnetic field. And you have 2 NV, you can have a signal that will produce the gradient. But basically it's 1 NV. So what I want to describe, it's another approach that we developed with my colleague Thierry Debuchert in Thales, which we call wide field magnetometry. This has been also developed in Harvard by Ronald Walsworth and his team. And it's somehow a much simpler system. So in that here, we will not rely on the resolution. Our goal is not to have to reach super resolution. We want to see the stray field with a resolution of about in the micrometer range, but we want to do it as fast as possible compared to the scanning system. The scanning system is great, but of course, resolution means also a lot of acquisition time. And now, for many applications, it's not what you want. You want to measure the stray magnetic field of samples that have typical size of a few micrometers. And for that, there is another approach, which is interesting and provides you with a lot of sensitivity. And we call that wide field magnetic imaging, or quantum diamond magnetometry in the AOS. So the idea is quite simple. We have a sample here in which we have on top of it that will be put just right on the magnetic sample. We will have a very thin layer of NV centers, okay? And what we can do is now excite this layer of NV centers with green laser light. We can do it by 2 ways. The first thing is here we would put a dichroic mirror and the dichroic mirror, we shine through the microscope. But somehow, if for certain circumstances, that can induce heating of the sample itself. And if you want to avoid that, you can use another trick, is that you have total internal reflection in the diamond, which has a huge index of refraction, 2.4. And that's not so difficult to realize. And then you're sure that somehow what you will have on just the evanescent wave, and that will decay very quickly. And if you are a few micrometers above the magnetic sample, you do not care about the intensity. That's a possibility. Now you have this diamond layer. You have the microwave excitation. So a very simple way to have this microwave excitation is simply to apply now a magnetic this coil, and this coil you drive current, the microwave current to it, and that will induce the precessing dipole. That will be our BX field somehow in our experiment. Then you collect the light that is emitted by the layer of the NV centers, and you focus it onto a CCD camera. Very simple. So you have the image of the NV layer on top of the magnetic sample, and at the same time, to remove any green parasitic light, you just put a bandpass filter, or notch combination notch filter that removes the green laser excitation and select only the NV luminescence. And I will show you how does that work with an array of permalloy microdot. So these are very thin, very soft magnetic material that can easily be magnetized with an in-plane magnetization, for instance, and it's what we're going to detect. Each plot has a typical dimension of 30 by 30 micrometer, but it could be much lower, and we will see much smaller, and we'll see example of that. So you have here an image. You see the dot here. That's the dot that you see here, okay? And here you have the image of the coil. It's taken really through the microscope objective. You see also that's the microwave coil. Huh? That's the coil here that you see. So what we see now, we apply the green laser, and you see the luminescence. We use that image was taken using this system, and you see really the light just emitting the layer of NV centers above one of those dots. And the dots were produced by our colleagues at Institut Curie. So I will show you now what we will have. Basically, the idea is very simple, and I hope that tomorrow we'll be able to show you a live demo experiment. So we simply now scan the frequency, and for each set of each frequency, we just record one image. So, and the image is just the luminescence of the NV centers that will be modified by the combination of the magnetic field, the stray magnetic field you want to detect, plus, of course, the microwave frequency. So what you have when we scan the frequency, these kind of things. You see some very strange shape that appear. Well, you would say that there's not much information around that. Actually, there is a huge amount of information in this set of image, and I will try to explain that. Okay? So why? In the NV center, we actually have 4 orientation. We choose, for instance, a 1, 0, 0 sample. So we have 4 NV orientation. For each, now if we look to 1 pixel, we can now use our set of image to now have pixel per pixel the microwave spectrum. So now this is what we would get, for instance, on one spectrum, and we would see, for instance, these 8 peaks. And these 8 peaks corresponds to the ODMR signal associated to the 4 possible orientation. I told you that what matters is a projection of the magnetic field onto the NV axis. So in our case, we have 4 projections of the magnetic field, and each of those projections will induce a splitting. So that's for one family. The blue peak here correspond to one family. The orange one to another family. The green one to another family. and the yellow one to another family. So from that, I can extract now 4 correlated measurements of the B field, of the vector B field, and I can use now, provided I have some information to remove some degeneracy in the response of those families, I can retrieve the 3 components, Bx, By, Bz of B. So this system allows me to measure directly the 3 B. So it's a vector magnetic field measurement. And this is very important. And this will bring a lot of information, as I will try to discuss. And another great advantage is, of course, associated to the fact that your time of measurement, you record the signal coming from all the pixels during the same measurement time. When you do a scanning experiment, you split your measurement time in a lot of tiny windows where you record the signal. So all experiment have sensitivity, which is set by the recording time. You want to have resolution, it means you have to spend time for doing that. In our case, we set a resolution which is about approximately the one also that will set by the distance of between the NV layer and the magnetic sample, but that can be as low as 1 micrometer, and then then the resolution somehow taking also into account the resolution of my microscope objective using the experiment, but it's not difficult to get a few micrometers of resolution, which is already great. But at the same time, the signal you have now has a huge signal-to-noise ratio compared to even a confocal scanning experiment that would somehow cut the time measurement in many, many small windows. So you have this multiplex advantage, and I will just show you now that it is a really quantitative. We can make really a measurement of the magnetization. So for instance, we have here the model of the micromagnet, of this microdot. We apply an in-plane magnetic field that will induce in the micromagnet a magnetization. So you have a magnetization like that, and what it produces, a dipole like that, on in-plane dipole. If now I look to the magnetic field, I know that the magnetic field will do something like that, okay? We'll have this shape. And now what you see here, for instance, if I put on top of it the NV layer, what I will see, for instance, is in this direction a magnetic field like that, and in the other direction a magnetic field like that. And it's exactly what you observe here. You see the component of the magnetic dipole, of the magnetic field created by the magnetic dipole, with the magnetic field Z components going like that and turning around the dipole and going in the opposite direction on the other side. And now also I can have the 2 measurements, and what I can do from that is fit those images by just a quantitative measurement of the magnetization associated to the magnetization that is produced in the dot, and you have a lot of tools of micromagnetism for doing that. And you can, at the end, measure a magnetization and at the same time determine the height at which we have the measurement. We realize the measurement, and that can be reduced. Somehow this parameter will set the resolution of your measurement system. And this parameter, which of course is correlated to D, the closer you will be, the higher the sensitivity, will set also the sensitivity regarding your magnetic measurement. And this is, when you say that, this is equivalent to 10 to the 13 Bohr magnetons, or 10⁻⁷ mu, and this is the sensitivity of a commercial squid. Actually, this is the signal we measure, so we are far above the limit here, but this is already the sensitivity. This is the limit sensitivity of most commercial squid apparatus that you can purchase. So you have a very simple system that somehow allows you to beat the sensitivity of a squid and that is what he explained in this system. And there are, I will show you later, after that, a lot of advantages of this technique in the very specific context of high pressure measurements. I will just finish very quickly because this is not long. So what you can do with that, you have a lot of possibilities that this opens. You can investigate micromagnets. That's quite interesting, actually. People are doing a lot of magnetic materials at microscale. There's a full chemistry. Many chemists are working on that. What you can do also is to detect the magnetic field which is created by a wire. And what you have here, it's the map extracted that is reconstructed from the current flowing in a wire. It's not so interesting, but you can apply the same thing now to detect the magnetic field produced by current in microcircuit. And this is something that we have done also with Thierry de Buchert and people in Grenoble at the CIA. So they provided us with the technique. And then what you have to do is a kind of reconstruction technique. So you measure Bx, By, Bz, and this is very important to get the three information for the efficiency of reconstruction. And then from the B is, as we know, related to the current density by the Biot and Savart law. And you can try to invert that. It's not an easy mathematical problem, this inversion. You have to take into account some constraint, but especially if it's not an arbitrary current distribution. But hopefully, you know a little bit where you are, your current. And from that, you get the distribution of the current flowing in your microcircuit. And this is quite important, for instance, to detect failure detection in microcircuits. And unfortunately, we didn't patent it. But now it's a product by Zeiss. It has all been employed after our work to do some very beautiful work to try to understand how the current flows in 2D materials, such as graphene or other materials. So it's really a tool somehow to investigate properties of current properties with a resolution in the micrometer range. And of course, the same technique could also be applied using scanning magnetometry. But for microcircuit, you don't care about. That would be the resolution is not what you want. You want to detect, for instance, a failure of the circuit. And this can be easily done with this technique, as you can imagine. Okay, and just to conclude this first part, that has led to a myriad of other developments. So I couldn't cover that. It's not possible at the moment. Each of them would be a given lecture, so, and maybe 2 lectures even. So for instance, people have used NV centers for atomic nuclear magnetic resonance. So now you want to measure the coupling to other spins, nuclear or even electronic spins that are just above the sample. And you can use a single NV center, or you can use the thin layer of NV center. There's a lot of possibilities on using that. You can associate that to microfluidic channel so that you can have a lot of experiments that are being developed on this direction. You can build also spectrometer, system that will measure magnetic field with that are tiny and that with the goal to compete at one time with the most sensitive system for that, which are based on atomic vapor cell that have a sensitivity of femtotesla per square root of Hertz. For the NV sensors, the best systems have now reached picotesla per square root of Hertz, but there can be other application. Then you can also, this is a beautiful work done in Delft and in Stuttgart in the team of Tamigno and Wartrup, in the teams of Team Tamigno and Jörg Wartrup, where people have used now the coupling to a nuclear spin. I will just describe a little bit how this coupling can be done. Carbon-13, nuclear spins, all that, and you can have a rich environment, and you can now address all these transitions and use them as a quantum simulator using all these spins that are used, and you try somehow to do something that competes with other quantum simulator based, for instance, on Rydberg atoms or other systems. I will spend now the half, maybe 3/4 of an hour to finish with, take a break, and we will continue after that with application of NV magnetometry to sensing under extreme conditions. And that's a work that has been done with a team at CA led by Paul Loubert. Thank you. Okay, so again, this will be more like a seminar. I will try to describe what we are, the main topic actually we are exploring in our team in Saclay, which is it's something that we pioneered with other colleagues a few years ago, which is using NV centers in the specific context for high pressure measurements. And I will first try to explain why high pressure physics is so interesting to my point of view. So, and what's the great advantage of using NV for these measurements? So when you look to materials at high pressure, actually pressure is a fundamental thermodynamic variable. With pressure, you can tune structural, electronic, and magnetic properties of materials. And I will give you some examples. And of course, it is crucial for Earth and planetary science. And that's why high pressure physics, why high pressure technology and high pressure science actually was initiated for exploring somehow in the lab the interior of planets. So to understand also why pressure is so important parameter, we can consider the free enthalpy Gibbs, the Gibbs free enthalpy. So it's just the usual term, the free enthalpy, U minus Ts, that defines the stability of materials. Oops. Okay. Oops, it's doing strange things. I don't know why. Okay. And when I look to that, now I had the PV term, the pressure and volume dependence. If I apply a pressure of 1 million of atmospheres, which is equivalent to 100 of gigapascal, then the volume change in the material, for instance, the dependence with pressure of the lattice parameter, times the pressure will be of the order of 10 electron volts. So that's more than any binding energy, most chemical binding energy. That means that new chemistry can happen. Very different compound can happen at those pressures, and I will give you also an example of that. Pressure has also been a very efficient tool to explore superconductivity. You all know that superconductivity, but it changed a little bit the size. I don't know why, because now it's here. Okay. Maybe we have to lower it. Okay. Whoops. Okay. So you all know that superconductivity was discovered by Kamerlingh Onnes at the early, in 1905, at the beginning of the 20th century. And then there was very slow increase of the critical temperatures of materials. We could reach something, and there was an important step to understand also the properties of materials was BCS theory to explain the superconductivity by the binding of electrons into Cooper pairs. And BCS theory tells you that taking into account Fermi levels, density states, there is a kind of limit around 20 Kelvin to 30 Kelvin. And that was actually what was reached, okay, up to that. So somehow all the compounds that were known for a while until 95 was something limited to 30 Kelvin for critical temperature. And then there was a real breakthrough by the discovery of superconductivity in cuprate material. And cuprate are ceramics. They are dirty materials. And Bernoz and Müller found that Labacuo was a superconductor with a great increase of the critical temperature. And that was, of course, a very surprising discovery. No one attended superconductivity, was expecting superconductivity in such dirty materials. Still, we do not understand where does this superconductivity comes from. It's called unconventional superconductivity, meaning that you don't understand anything about what's happening in that. It's not exactly true now. There have been a lot of studies. But still, after more than 40 years, almost now 40 years after, we still do not understand why the physical reason that makes those materials superconducting. And then just after that, there was a great step done by Paul Shu and his collaborator in the US, which was to apply pressure on this material. And they immediately saw that the TC rose rather significantly by applying pressure. And so they had the idea that somehow you can mimic this pressure by what they call chemical pressure. And the chemical pressure is somehow you change one compound on the one compound of the atom, and that will mimic the external pressure you apply just by internal constraint in the crystals. And so they had the idea to change lanthanum atom here by yttrium atom, which is smaller. And going to the smaller size of this system will increase the temperature remarkably above the liquid nitrogen temperature. And evacuo is the superconducting at temperature above liquid nitrogen, and that's why we can do a lot of, for instance, demo experiments using this material very easily. It's also difficult to produce. Basically, if you have an oven, you take the different samples that you have here, and you crush them, you make a pestle, and then you cook it for a while, and you get your evacuo sample. Paul Shu also discovered other material, and especially together with other people, he was able to achieve the highest critical temperature for a long time, which was obtained in a mercury-doped cuprate, and we will work on that. We will show you results that we have done on that, at a pressure of, and the highest critical temperature, about 165 Kelvin, was obtained at a pressure of 30 gigapascal. That's one point. And then there was another breakthrough, which is now still under strong debate, which is a new family of material. BCS theory tells you that somehow superconductivity will be far improved if you could have very light material. And then you can think of the lightest atom you can have. It's hydrogen. And following this idea, Neil Ashcroft proposed that hydrogen would be superconductor, but at pressures where first it is metallic. And metallic hydrogen was expected to occur at amazing pressure. It was predicted in the 30s by Wigner and Huntington and the pressure range. But then up to now, no one really has been able, until maybe a colleague, Paul Loubert, with whom we collaborate, was able to achieve a metallic state of hydrogen. Perhaps what he has achieved is a metallic state of molecular hydrogen. So there's a lot of still, but the pressure you need to reach that is 400 gigapascal, higher 4 millions of atmosphere. I will show you how this can be realized. And Neil Ashcroft predicted that if hydrogen is metallic, so unfortunately at those crazy pressures, it would be a superconductor following BCS theory. But then there was a second step, again a little bit like the idea of the chemical pressure, was to now add another compound with hydrogen. And somehow to address other samples, which are called hydride, in which somehow the structure of the crystal is very close to the one you would have with hydrogen. And those systems were expected to be also superconductor, following the calculation that was done by the prediction of Neil Ashcroft. And this is hydride is somehow the combination of a metal plus hydrogen. But to get that, you need to be at high pressure so that you have samples that have this very specific stoichiometry and structure that is specific to the onset of superconductivity. Sorry. And it was found that indeed superconductivity was first found by Michael Eremets and his team in Mainz in 2015, 10 years ago, in sulfur hydride. That was indeed predicted in this material by ab initio calculation. And it was observed using resistivity measurement. And that was a very landmark paper. And the critical temperature immediately rises very significantly, 200 Kelvin at a pressure of 150 gigapascal. Of course, the question is, I will discuss that at the conclusion, what can you do at such pressure? Is it an interesting material for any application at those pressures? Let's put that aside for the moment. And then there was another great step forward done by, again, Michael Eremets and also Russ Emley in the US, where they observed superconductivity in another system, embedding even more hydrogen, lanthanum hydride, LaH10. And this is somehow a structure. You see here the lanthanum atom, and around the lanthanum atom, the hydrogen atoms are organized in cage, and this leads actually to a physics close to the one that is expected for metallic hydrogen. So, and the TC is around 260 Kelvin at 200 GPa. And now, today, there has been a systematic computational exploration of binary compounds, and evidence for superconductivity has been found in approximately 10 compounds. So we would like now, again, to reproduce all these experiments at high pressure. And why do you want to do it? First, all these experiments are realized with this remarkably simple tool, the diamond anvil cell. So the diamond anvil cell consists of two diamonds with a shaped cut and shaped with a tip. The tip has a diameter that can go to 500 micrometers to a few micrometers. For instance, people that want to achieve 400 gigapascal, they will work with a diameter of the cullet of the tip of the anvil, we call that cullet, that will be around 20, even 10 nanometers. So you can imagine how the system will be. So the two anvils, we will squeeze them against each other. And inside there will be a pressure transmitting medium. The material will be embedded. And then that will be used to apply hydrostatic pressure forces onto the sample itself. And there is also a lateral confinement that is ensured by a metallic gasket. So it's something that is done, for instance, in rhenium. Rhenium is the metal that has the highest stiffness. And you drill a hole in the gasket, in this metallic gasket. And this is, again, squeezed with everything inside. And at the end, you have this system. And what's remarkable is that at the end, it's like a bottle. You can imagine my bottle here. I have these two tips like that, the gasket in between. But now I can take it in my hand, and I can go to whenever I want. I could have brought it here. I could go to a synchrotron, for instance, and do X-ray measurement to identify the structure of those materials. And actually, this is what has been done. So it's a very practical tool. You can even control the pressure in situ by controlling the force that is applied on the outside of one of the anvil. And for that, we have here a membrane, and we insufflate gas in the membrane. And just due to the difference of surface here to here, we control like that the pressure inside the cell. And the pressure is controlled here with this tiny capillary tube that you see here. And there's a tap here. You close the tap, and then you can have your sample at 100 gigapascal and keep it forever if you want. And there's almost no leak, of course, because if there is any leak, then everything will be removed. So this is very nice, and this has been found in the 50s, and there has been a lot of technical development on how to use the anvil. There have been remarkable discoveries found using this tool. Now, what you want to have also is diagnostics. You want to measure superconductivity, that your sample, after the pressure, due to the pressure that is applied on it, becomes a superconductor. So, of course, you have one approach. It's to put electrodes and measure the transport properties the resistivity of your sample, and you should see that it drops to 0. You can imagine that you have now to put very tiny electrodes. You need 4, for instance, to avoid any bias in your resistivity measurements, and that will go onto the sample. And this is very difficult. Of course, what can also happen is contamination of the sample by the electrode, and this is very hard to reproduce. And somehow, making this electrode in this environment is a kind of art by itself. That's one property, and also you probe again the whole ensemble. You don't know, so you can have something that decreases the resistivity, but getting null resistivity is always very difficult. So this is not a very, it's an evidence for the existence of superconductivity, but you have to demonstrate something else. And what you have to demonstrate is that the specific properties of magnetic properties associated to a superconductor, which is a perfect diamagnetism. So you measure the magnetic susceptibility. And that can be done using roughly 2 main techniques. The first one is that you have an excitation coil, and using a pickup coil, you measure the response from the sample. But you actually measure the response from the sample and also the response of the system itself. Everything is the outside. So it's also, again, an ensemble measurement, and the sensitivity due to the dimension of the sample, which is very small. The sample will have the typical size at a pressure of 100 gigapascal of about 10 micrometer. You can be due to the constraint of the system. Basically, you are limited in sensitivity. The other approach is now to use the most sensitive magnetometers so far, that are squids material. And those squid material you want now to integrate your diamond anvil cell into a squid apparatus. The squid apparatus has a very tiny diameter, so it means that you need to make very specific diamond anvil that are non-magnetic, and that can be integrated into this system. And that's, again, very, very challenging. So with all these techniques, you do not have any spatial resolution. You probe the whole sample. You can have sample by contamination. And in the all magnetic measurement, it relies on a large background subtraction. The signal over background is typically 10⁻⁴. So you want to see a negative magnetic response over something which is a background of 10⁴. And this is very, very challenging in the data analysis. So all that led to a fierce debate on data interpretation, even questioning the existence of superconductivity. And there was work done by some theoretician, Jorge Hirsch and other two or three other people, that somehow looked very carefully to the data. And they even found that one of the main claim of high pressure superconductivity that was done by someone in the US was actually completely false and was a great scandal somehow, a vast fraud about that just by looking inside. I do not say that superconductivity in superhydride do not exist. What I want to say is that we need to confirm it and to have a reliable way to probe it so that we can compare efficiently measurement done in one team to measurement done by another team, which is definitely not possible with those techniques. This is a kind of expertise that only a few teams in the world can have. And of course, you want experiment to be confirmed, you want more experiment, you want more sample to be explored. So our approach was completely different. Of course, you know that associated to the diamagnetism of a superconductor, it's actually the Meissner effect. And the Meissner effect is the expulsion of a static magnetic field from the interior of a superconductor, with this picture that you already seen. So what we want to do now is would like to have some compass integrated or close to the sample that could be used to monitor the field distribution very close to the superconductor and observe in real time when we cross the critical temperature that the magnetic field becomes now uniform all over the sample. And for that, of course, you may have imagined what we want to use, is to integrate the NV centers and use them as in situ magnetic sensor on the tip, on the anvil tip, to measure this distribution of the magnetic field. And that will allow us to really go in to analyze how the magnetic field interacts with a superconductor, and that avoids all kind of bias that are exist, that could avoid the main bias on that. So what I want to do now is to show you how we implement this very simple idea. And the very first, we have to create the NV centers. But at that, as I mentioned, we have this remarkable tool developed by Martin Schmidt in our team, where we have now, we can implant the nitrogen atoms, convert them into NV centers, and you have here, on an anvil tip of a diameter of 300 micrometer, just arrays of NV that were produced with a pitch of 10 micrometer. Each NV dot has a diameter of 2 micrometer in this experiment, or just a layer of NV uniform with uniform density that can be used for wide field NV magnetometry, as I showed you before. So we do that, and now what you simply have to do is basically to implement all the tool I discussed with the constraint of a diamond anvil cell. And the first, so basically the idea is very simple. Diamond is transparent, so we can excite the NV layers through one anvil and collect the light emitted by the NV layer through the anvil again by the same microscope objective here. We have to apply the microwave excitation, and for that, we wanted from the very beginning to avoid anything inside the coil, inside close to the sample, and to have a microwave excitation as homogeneous as possible. So I show you in the implementation of wide field magnetometry that we use these simply a coil consisting of 2 turns of copper wire. So we simply do that idea. We'll put on top of the gasket this microwave wire that we do ourselves and hope that it works. When we tried, we didn't work at all. We saw no NV resonance. And then we thought a little bit, and then we found a reason for that. If you put something on top of a metal, it will induce eddy current in the metal. In France, we call that courant de Foucault. Foucault's current, in English, eddy current. And when I was a student, I always thought that that was the current coming from Mr. Eddy. But that's not the reason for that, because okay. So now we change, and basically we have that. And the magnetic field and that is produced by both the current in the wire and the eddy current in the gasket compensate, and we have B equals 0 as expected in a metal, but also in the interior here where we have the NV center. And then we had the idea, okay, let's provide that. So we cut now, we prevent the eddy current by making a slit. And actually, we're very proud of that idea, and we found that that was also already invented a few years ago by Ike Silvera in Harvard. Okay, nevertheless, actually, this simple idea worked. We were happy about that, and then we thought a little bit again, and we found that the slit was actually very acting in a way more subtle than we thought, because somehow the eddy current will be redistributed, and somehow now close to here, you see that they turn the same way as the coil, as the current in the coil. So somehow it's a way to focus the microwave excitation, and that's what we also discovered that this was already found by many people, and people call that a lens, L-E-N-Z, lens. Okay, a way to focus by induced current a microwave excitation, and that was implemented in microcoil for NMR. Again, many people are clever. Then what we thought after that is, of course, you may say now we have the slit. First, you fill it with whatever you can. So it's HBN powder or diamond powder or whatever, and then epoxy glue. But this is not working so well. So either the slip opens, and then that was a complete failure, or the slip closed. It was again a failure. So you have to find a design So we worked a lot on optimizing the design on the slit, and we found that somehow with this shape we can go up to more than 100 gigapascal with a very stable shape of the slit. And the slit is cut with a femtosecond laser. So we have a femtosecond laser, and we can design the shape of the slit that we want using this system. Okay, and then you see here, again, another view of the slit cut in the metallic gasket. What I want now to show you is a recent experiment. So we did that for a long time. I forgot something. Oh, yes, I forgot one slide. Okay, so let me see if I can add one slide. That's strange. Just I remove it. I was too quick. Yes, this one I should add. It was too quick when I removed the slide. Okay, so now we somehow can do NV magnetometry in diamond angel cell. And in 2019, there was actually 3 papers published back-to-back in Science, where we show both that indeed this technique can be used to measure magnetic properties, and at the same time to measure superconductivity. The 3 teams were our team at INS Paris-Saclay, working in collaboration with Paul Loubert's team at CA. The team of Norm Yao in Berkeley at that time, now is a professor in Harvard, together with Raymond Jeanlos, who is a high-pressure expert work that has done really a pioneering experiment in earth science. So using diamond anvil cell, he was able first he was the first to mimic earthquakes. So, and basically he used, he could put some microphones somehow techniques to understand cracks occurring in rocks that were mimicking the occurrence of an earthquake. So he did this work, which was remarkable, and many other work. Paul Loubert did this remarkable experiment recently on metallic hydrogen. And that's the team in the US. And the other team was in Hong Kong, led by Shen Yang at Chinese University of Hong Kong. Now he's at Hong Kong University of Science and Technology, together with Sui Go, who was also was an expert of quantum materials and was applied for his research a lot of high-pressure techniques. So it's always a combination of people that have knowledge of NV centers plus people having the knowledge of high-pressure techniques. So in our case, for instance, what we did was to investigate a well-known pressure-induced transition occurring on iron. So if you have iron, you know that iron in our conditions can be ferromagnetic, and that's associated to this specific crystallographic structure. But now if you go to higher pressure, even at ambient temperature, you go to this new phase of iron, and in this phase, iron, there is not anymore ferromagnetism. There is no magnetism at all, and the reason is not completely clear, even now. So there's a lot of studies to understand what the reason for that. Nevertheless, we said this is a nice testbed system. So what we do is we have here inside the sample little beads of the iron, and we apply pressure on them. From the bead of the iron, we magnetize them with this technique. And again, with our 4NV orientation, we can really directly see the magnetic field arising from the bead. We can even go to a really quantitative measurement by, again, the same approach as I show you with the permalloy dot. And when we increase now the pressure, the magnetic field produced by the bead will get smaller, 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 and smaller until it disappeared. And if we release the pressure, we see that the magnetic response starts again. There is some hysteresis due to the size of the bead and the fact that it's certainly non-monocrystalline, a single crystal, but we could see that until at one point we do not have points afterwards because we broke the anvil. That sometimes happens. And then another experiment we did That are results that were obtained in Norm Yau's team on gadolinium. At the same time, we were looking at can we observe the superconductivity through the direct observation of the Meissner effect? And this is our proof of principle experiment. We put in the anvil here a system where we have now a powder of MgB2. MgB2 is a well-known superconductor that has a pressure, and its critical temperature will change with pressure. And what we see is below the critical temperature, we apply a magnetic field like that. And the magnetic field in the z direction will have the same projection on the 4 axes of all 4 families that I have. This is important. So what I see, all 4 families will have the same Zeeman splitting. And now I plot the Zeeman splitting here as a function of the position. And this map is directly obtained by wide-field magnetometry. And what you see here is that on this point here, sorry, let me see, poof. Okay, what you see here, okay, it's the fact that somehow the magnetic field is excluded from the superconductor. So it means that the NV here do not see anymore a magnetic field, or a magnetic field which amplitude has been strongly decreased by the Meissner effect. And this is exactly what we observed here when we looked to the Zeeman splitting. The Zeeman splitting here is much smaller than the one that we have at the outside of the sample. Okay? So here we have a direct proof that there is expulsion of the magnetic field. And now if we increase the temperature, this expulsion will become weaker and weaker up to a point where we now have a uniform distribution of the magnetic field that's experienced here. And from just measuring the Zeeman splitting on top of the sample, we have this curve, this shaped curve, and we can determine from that the critical temperature of Tc, and this critical temperature is 30 Kelvin as observed, measured for this compound with other techniques. And that was done at a pressure of 7 gigapascal. Okay, so that's a kind of proof of principle, but now what we want is to go beyond that, is really to analyze what really happens carefully, and especially to detect the magnetic field penetration in the sample. And so for that, we studied, that was the work of Cassandra Daiduz as a PhD student during those 3 past years. And we used a sample, very good sample, that was grown at CA by Dorothée Colson and Anne Forget. So what we have been doing is reproducing the experiment by Paul Shu in the 90s. And of course, the great advantage that those systems are stable at ambient pressure. They do not require, like these superhydride, to be synthesized at high pressure. So we introduce them in the diamond anvil cell. So you see here the structure of the compound. This is here the compound of a small flake of these cuprate superconductor. You see here, that's the gasket. And you see here the slit here in the gasket. Okay, the main element that I've seen. And everything is filled with a pressure transmitting medium, which is argon gas. But of course, as soon as you apply some pressure on it, it becomes solid. So now we do the experiment. So this is an image of the flake, which is a little bit, as you can see, which has some homogeneities that you can see here. And we integrate it here, so it's the scheme, and we study it, again, using wide-field magnetometry. So you see the different steps, the different elements, as I showed you before. And this is now the PL intensity recorded over the sample. And what we do is apply the same technique as I discussed. So we record at a given temperature, we scan the frequency. We record for each scanning frequency the intensity map recording using the CCD camera. And then we simply change slowly the temperature. And we have all these set of information that we can now reanalyze afterwards. That's a huge amount of data. And it was not clear how to use them at best. in a very practical way. So I will try to explain how we do that. So this is something which, to seem that strangely, is perhaps the first time that people have really mapped how the critical temperature is distributed in a crystal. We can do the experiment on one point, like for instance, choose one point above the superconductor. Let's say, I think it was something like here, if I remember well. And we measure, like before, the evolution of the ZPL, of the magnetic resonance of the NV center for the 4 families with a small magnetic field that is applied of 3 millitesla applied along the z-axis, and the z-axis is also the 1, 0, 0 axis of the diamond field. So what you see is that the magnetic field, we have 2 ways to do the experiment. The first one is called zero field cooling, and the other is field cooling. We'll try to explain the difference later on. In these 2 regimes, we observe the same behavior. You see a sudden a signal that is an ODMR splitting, which is strongly reduced, and at one point, which becomes uniform, the same value outside the crystal. And from this evolution, we can infer the critical temperature here, and we have the same value for the 2 protocols that are used, and I will explain them. And we can do some map of the magnetic field of the TC, because we're using our data, we have this information all over the sample. So we can do the TC map, and we can have the value of the TC. Of course, there are parameters that are outside, values that are obtained outside due to the Meissner effect that creates a distortion of the magnetic field distribution even outside the sample, but this is not relevant data, of course. And we can see now that the temperature, the critical temperature in the sample, above the sample, will change by a few percent regarding what the average value. And all the data analysis is described in this paper. So, what is the difference between field cooling and zero field cooling? The zero field cooling is something where you have your sample, you cool it down much below the critical temperature, and you apply the magnetic field. And you see now, then Zeeman, the Meissner effect occurs, and you see how the Zeeman effect will disappear when you cross the critical temperature. Okay? Now, the field cooling regime is different. You start from non-superconducting state at temperature above the critical temperature. You already applied the magnetic field, and you cool it down. So somehow the system will keep the memory of the magnetic field, and you have it down here, and then with the magnetic field on, now you increase again. So in that case, you see that there are slight differences that have appeared if we compare, for instance, this zone. We see that the 2 regimes do not provide the same information. And why for that? And the reason for that is that actually the magnetic field, if there are inhomogeneities in the sample, the magnetic field that is applied during the system, during the cool down, can penetrate already into the sample due to the and somehow create little zone where there won't be the Meissner effect, and this is what you observe here. So this is, for instance, can be due to trapping zone where the magnetic flux gets trapped. And so you can confirm that by a 3rd experiment, which is called the flux trapping experiment, and this is perhaps what I think the very beautiful experiment, in the term that now what we do is that we apply a magnetic field, okay, when we cool down the system, like before, but instead of now heating the sample with still the magnetic field, we remove the magnetic field. Now we have launched somehow some superconducting current inside the sample, and those superconducting currents can survive for almost whenever. And that in the experiment, I say that this superconducting current launched in a superconductor can stay there for years. So we try to do, now this is what we have done. Somehow we remove it, and we try to see what happens. And what you see is that the superconducting currents create some areas just above the sample that emits some magnetic flux, that create the magnetic flux. And somehow this is due to some current here circulating that exist somehow, that were responsible for the difference between the field cooling and the zero field cooling image, that were due to magnetic flux really trapped inside the signal. So that's another proof of existence of superconductivity, at least for for type 2 superconductors. And now if we increase the temperature, then the system will go to this superconducting current will decrease progressively, and it will disappear. And from that, from this evolution with temperature, we can also determine the critical temperature in good agreement with the value we obtained before. Okay, so, and this correlates well. The zone where the magnetic flux is trapped correlates well with the area where we could really see a strong difference between the two images we obtained, both with zero field cooling and field cooling technique. So now we have all this set of methods which we believe are very powerful and with efficiency has been really proved by us, by other persons. There is a lot of work now done in China applying our techniques, applying this technique of NV magnetometry for high pressure experiments. But the question I would like now to address is there a pressure limit? And that was an important point. We want to apply those techniques to investigate, for instance, the superconductivity of superhydride that exists at pressure above 100 gigapascal. And let's see what happens. So this is experiment which was done again with the same sample, the same compound, at 1 gigapascal, and now at 30 gigapascal. You observe that the contrast of the ODMR signal is strongly reduced, up to a point where basically, if we increase a little bit more the pressure, we cannot see anything. So somehow the signal, the NV signal, deteriorates with pressure. And that was, people thought that this would be a kind of practical limit for NV magnetometry, somehow around 30 to 40 gigapascal. So the question is, why does the NV Meissner signal deteriorate at high pressure? And can we maintain the signal at pressure above this practical limit? And if we look more carefully at what happened to the NV in the tip, we have to realize that the NV are in a stressed environment. And NV centers are sensitive to many parameters through the dependence of the lattice, but they are also very sensitive to the strain or the stress that is applied around us, of the matrix in which they are located. So, of course, when you build your cell, you have to do very accurate adjustments so that the two anvils are perfectly parallel to each other. If there is any mismatch of angle, when we squeeze them, immediately it breaks. So we take great care in the adjustment that the two anvil tips are really parallel. And this is observed, for instance, in this observation here. You see that there is no, there's a uniform light going here when we look through the anvil. But when we now apply the pressure on the tip, you can imagine that there are huge forces that concentrate on the tip, together also with the huge forces that are exerted laterally by the tip. So what happens is that the tip becomes, the anvil tip has now a curvature. Okay? There's a cupping effect on the tip. And this cupping effect, due to the competition between compression on one side and surface tension on the other side, leads to this shape of specific shape that you can really observe. This is the distortion here, the fringes here, tells you that you have indeed these interference, this shape of the diamond anvil. So since we have now the NV centers at the really above the tip, what will happen at the surface of the tip, what's going to happen is that those will have a strong stress that is applied not on their axis. So somehow we will have the NV center that in an environment which is non-hydrostatic. That's what we think. So if we do that, we can model this effect by applying a stress tensor at the anvil tip, which is quite simple. We say that in the z direction, there is a pressure that is applied. And on the transverse direction, due to the cupping, we have it is reduced by a parameter alpha due to the surface tension. And alpha should be below 1. So from using that, we now integrate that into the Hamiltonian. And once we have that, we can measure now the Z-man dependence as a function of this model. And we clearly see positions of the resonances that's in very good agreement with this model and the alpha parameter, which is around 0.6. And you see two effects. You see first this effect, the mean frequency is going up. Okay? And this can be understood very simply. I have the two electrons of the NV. When I apply pressure, they get closer and closer and closer. So I strengthen the magnetic dipole-dipole interaction between the two electrons, which leads to an increase of the D parameter. Okay? But at the same time, the non-hydrostatic stress, transverse component of the stress, will mix now the quantum state plus and minus somehow, will mix the state of the basis ms equals 0, plus 1, and minus 1. And this will somehow induce this shape dependent. And also, we believe, also we do not have a model for that up to now. We believe that this will also induce the decrease of the ODMR contrast due to this strong mixing effect. So somehow, but this we don't know. We would have somehow to reproduce all what we know, and especially the intersystem crossing and the metastable singlet state. But this, unfortunately, we were not able yet to do it. We don't know how these non-hydrostatic pressure affect both the singlet state and the intersystem crossing rate. So we left that aside, and we try now, we say, okay, the problem is a non-hydrostatic stress. If we now are in hydrostatic condition, we preserve the intrinsic symmetry of the C3V, C3V symmetry of the defect. The MS0 plus minus 1 will remain the good basis of the system, so we could expect that the ODMR signal will be kept for even at very high pressure. But can we realize that? And our idea was just to mill with a fib or femtosecond laser a pillar on the anvil tip. So somehow that will decouple the pillar from the compression from the cupping effect on the anvil tip. That was the bare idea. So this is a pillar. It's a stiff pillar. It's wider, a few micrometers, and just a thickness of 1 to 2 micrometers, rather stiff, but enough, we thought, and we did some calculation about that. Also, it's quite difficult, but nevertheless, we convinced ourselves that geometry could be efficient for doing that. And the third check is to look at the Raman signal of the diamond. The Raman signal is already a good signature, whether or not to get an insight of the stress environment. So if we look outside the sample, we have this typical signal, and that typical signal can be explained by non-hydrostatic conditions. If we now look exactly on the pillar, we see a new peak that arises, and this new peak with a higher Stokes shift, a Raman shift, is actually evidence that there is a higher pressure somehow exerted here compared to here, on the red dot compared to the blue dot. And if we now look to the evolution of this small peak on top of the pillar as a function of pressure, it follows very well the dependence that was found in hydrostatic condition for the diamond Raman shift. So somehow this is the first evidence that this is an evidence that indeed our pillar technique provides us a method to retrieve hydrostatic condition. So now let's look to what happened to the NV signal. And you see that we keep the Z-man shape. The Z-man dependence is kept now. We do not have anymore the mixing of the state that says to this great splitting even at non-zero field. But there is only now a shift of the D line associated to the dependence of D parameter with pressure, so two electrons simply getting closer. But nevertheless, the C3V symmetry is maintained, and we keep the ODMR contrast. It decreases on this branch, but the decrease is simply due to the fact that our microwave excitation was not efficient above 4 gigahertz, and that was somehow a practical limit. But now we've been able to purchase new equipment and to work with more to get contrast increased at those pressure range. So somehow, and the fit give us a value which is close to unity, saying indeed that we are close to hydrostatic conditions. So somehow, we can now have a method to maintain magnetic sensing behavior unchanged up to 103 gigapascal. So it's no longer a limit if we want to explore the superconductivity of superhydride. And this is now what we're trying to do. It was confirmed in microdiamonds by putting microdiamonds inside the sample with the signal that was observed at that pressure, but perhaps not as convincing as the one we had. But nevertheless, it was also an independent proof. And there was another approach that was complementary to us that was done by Norm Yao and also people in China that use now 111 anvil. And those 111 anvil, you have one NV family in which you apply the pressure exactly on their axis. So for that family, it's really great because everything is perfect. You keep their symmetry by construction somehow. So it's again another proof that it's indeed the C3V symmetry that matters in everything. And Norm has applied that for a very nice experiment, which shows some kind of first evidence that superconductivity can be observed in superhydride using the NV technique approach. So that's very interesting. And at the same time, Jiang Fengdu in Hefei and Chinese Academy of Science reproduced the same idea, implemented the same idea, but now done, and the paper has been published in Nature Communications, I should put it, that was on some other magnetic materials that have a phase pressure-induced transition above 100 gigapascal. Okay, so we can compare, for instance, benchmark our technique to SQUID. And of course, it's rather difficult to always say I'm better than another technique. But I would like to highlight two main differences. The first one is we're able to work in the same range. And we do not need specific cell. We have a sensitivity that we believe is higher. We have no background. This is some important advantage. But more than that, what we can do is really map the critical temperature. So we can deal with inhomogeneous sample. That's something quite important. And most of as soon as you apply pressure, you can imagine that there can be inhomogeneities created in the materials. Or even if you get the materials from a chemist, that will be certainly non-perfectly homogeneous. It will take years to improve the quality of the materials. So, and to put all the effort on the development. At the same time, the NV magnetometry system that I show you, especially the wide field system, is so simple that somehow we can build a portable apparatus and take it and bring it, for instance, on a synchrotron beamline. And in this experiment that we published a few years ago, we did that. So we observed the alpha to epsilon pressure-induced transition of iron on a synchrotron beamline. So we could do at the same time the measurement by X-ray diffraction of the evolution of the crystal from the alpha structure to the epsilon structure and measure simultaneously the evolution of the magnetic response. And I think this is very important because as soon as also you get some materials, you want to analyze the structure. And now with 4th generation synchrotrons, you achieve resolution in X-ray diffraction pattern at about with micrometer resolution. You can really determine the structure of a sample with this micrometer resolution. And somehow having a tool that measures the magnetic response with the same spatial resolution is something that will be very complementary for all these measurements. Okay, we can apply the same technique to investigate how pressure acts on other defects of diamond. So for instance, silicon vacancy, germanium vacancy. So this is crystals, nanocrystals that embed these defects. You integrate them and you observe and you try to observe, for instance, how their spectrum will change with pressure. This is a very preliminary experiment. But remarkably, our data fit very well with ab initio calculation that were done by Adam Gali and Lukas Razinokova's teams in Budapest and in Lithuania. And we observed that, for instance, there is a very good agreement between the evolution of the ZPN line as a function of pressure up to almost 200 gigapascal. So this tells you that indeed we can really play now with a lot of parameters and understand, for instance, the structure of defects using pressure to confirm, using ab initio calculation, really the structure that is observed. Okay, so this is just an overview of what we're doing, and we're building, and we hope that in the future many results will come from applying NV magnetometry to the specific context of high pressure measurement. And this is just to show you the team involved in all that during the past years. So my colleague Martin Schmidt, with whom we worked really for a long time now, and we build the NV signal, the implantation machine together with also Margarita Lezik. Margarita Lezik was a PhD and postdoc in the team and left a few years ago, and she's now in charge of a team in a industrial research lab. Marie-Pierre Adam, who is a research engineer in our team, and we do a lot of development and experiment at the moment. And we have two setups. I hope to show you them tomorrow. One here with Cassandra and Claire, Cassandra Daidous and Claire Roussy. It's you have here a small cryostar. You don't see it very well. And here, the NV microscope head on which we can do very easily NV wide field or confocal microscopy. And this is another system. Grégoire Le Carrière de Beauvais, a PhD student here with Kin On-O, was a postdoc for 1 year and a half and is now in the US, coming from Hong Kong. And we have a system here. So it's a cryogenic system from Attocube that can go down to 2 Kelvin. And at the same time here, we have superconducting magnets. We can apply 0.5 Tesla in every direction we want. And Grégoire was able to build, all the optical setup and microwave delivery that can now be used on this system to test superconductivity and other properties of materials at both low pressure and under high magnetic field using NV technique. And that's where somehow all my funding comes from the team. An ERC grant. ERC is a European Research Commission grant. And EUF, that's something in France where basically you are free of teaching for many times to really concentrate of your research. INR is our funding agency, a national French funding agency. And this is something that provided us a support for a lot of purchase of materials, especially to settle the high pressure center and all the instrumentation that is required for the assembly and technology for the NV for the high pressure diamond and cell techniques. And Quantip, it's our federative center in Île-de-France region around Paris that provides support to the development of science and quantum technology. Thank you for your attention, and we will have this afternoon the lab demo.
So there is time for this and not for this session.
And if you have questions, do not hesitate. We have okay.
Okay, so we need around 2:30 for the lab demo. We'll update you.
हेलो हेलो।
वो नहीं मैंने दिक्कत क्या है उससे अगर डालने की? एक बार लगा के देखो ना, मेरे हिसाब से सब अच्छा दिखेगा। ये जो आप ये दिखाना चाहते हो ना, ये hello, hello.
दिख रहा है सबको presentation? You can see a presentation? Okay. माइक ऑन कर दिया, हाँ? सही है? नहीं ठीक है. So, all right, so welcome to the demo lab. So the plan is today that I will give first a brief presentation about what demo we are going to show here about the nano diamonds. And the demo experimental part, Priya Yadav, she is a PhD student, third year PhD student. So she will show you the demo. She will also participate with me in the demo. So the idea is that as we have learned that NV exhibits fluorescence. So we have here a very basic setup to measure the fluorescence starting from scratch. So we will demonstrate various things. The idea is that first we will show you the basic experimental preparation. So that is actually the setup here. And then how do we make NV sample? So we actually purchase the colloidal solution of nanodiamonds and then we put them on slide. Then we will describe the setup. So it is basically a custom made microscope setup. You can see everything is like assembled here and we can change various parts and we will explain you all the parts one by one. Especially what are the lasers, optics, what are different detectors, spectrometer, and also the microwave excitation. The microwave part we will not be able to demonstrate right now, but I'm just showing it as a part of the setup. And after describing the setup, we will make certain observations with you step by step, looking at the NV sample slide, then exciting them with laser, then the fluorescence, then capturing the spectrum. So we will go up to that part. And finally, I will discuss some components of the ODMR, but the setup is not yet ready for ODMR detection. So after this demo, we will try and hopefully we can show you next time. Okay, so the sample preparation starts with a commercial colloidal solution. And maybe I will just give a brief overview, then you can demonstrate them. How do we do? So the specifications from the manufacturers are that this solution has 120 nanometer diameter nanoparticles on an average. And typically it is 1 milligram in 1 milliliter of deionized water. And the concentration of nitrogen vacancy is 3 ppm. Okay, so 3 part per million. And then what we do, we start with the drop casting that solution on a cover slip, and we can spin it to make a uniform, like almost uniform deposit, or we can leave it as it is for some crude observations. And you can see in the picture on the right, this is actually the nano diamond deposited on ultra thin glass. So ultra thin glass is 30 micron thin glass, which is now available in our foldable devices, right? So you can see that, and for this picture we took the glass and then cut with the laser. So you can see the side view. So side view is like that, and you can see the glass thickness is 30 micron, and on top there is some white layer, nano diamond layer, which is about a few micron thickness. And how do we know that the solution we have is actually nano diamond? So we also do some basic structural characterization. For example, one can do the transmission electron microscopy. So if you know about the TEM, then it is like we have a TEM grid, and then you take the nano diamond, deposit, and then put it under the transmission electron microscope. And there one can see that we can zoom in and one can see the lattice spacing, right, 2.06 angstrom. So these are actually a proof that there are some crystals inside. The resolution of TEM, however, is not enough to actually measure the vacancy, right? And also the TEM will just show you the two-dimensional picture of the nano sample, right? But it's showing that we have the nano diamond crystals. And we can also do the XRD, and you can see the XRD, we have a very specific peak at 111 location. right? So this actually proves that there are nano diamonds in the sample. In addition to this, we can also do supplementary measurements like Raman or FTIR, right? Okay, so this is the basic setup, and there are different components in the setup. So that actually she will explain. So, and the basic idea is that we will excite the samples with a green laser, as Professor Rock told, that and we absorb in green, and then it emits in the red fluorescence. So we will then capture the fluorescence and measure the spectrum. This is a typical image of one NV center, not single NV center, but one spot on the on the on the sample, right, excited by the laser. We will see these images live, and these are the spectra, and we will also try to measure the spectrum, and you can see there are very specific the zero phonon lines, NV0 at 585, then we have zero phonon line for NV -1, and these are three different spectra for three different laser powers. As we increase the excitation power from 6 microwatt to 10 microwatt and then 20 microwatt, right, you see the fluorescence is increasing, obviously, because now more and more photons are exciting the NV. And we are way below the bleaching threshold. So if we reach the bleaching threshold, then of course everything will collapse. This is another experimental parameter that we can tune, because in the spectrometer we also have a possibility of acquisition time. So you keep the power fixed and change the acquisition time. So that also improves the spectral collection, and it also shows that the counts increase with more exposure time. Okay, this is some cross check, because as we see, the defects are very common in most of the systems. So we put the NV on the glass slide, and how do we know that the observations we are making is not because of the defects present inside the glass, right? So for that, this was the question asked by us from the referee. So for that, what we do, we take the glass and observe the fluorescence without NV, the left side picture, and you can see the laser power is 5,000 microwatt, so it's about 5 milliwatt power, and we see very little counts of NV, like 20, 25 counts from the background. And in this work, we also cut the glass with the femtosecond pulse. So there is also possibility that the femtosecond pulse can also induce some defects in the glass, right? So that we see some signal, but it is very weak. And on the same slide, if we deposit NV and capture the fluorescence, then you can see the counts are huge, right, 1800. So even though there may be some background counts, but they are very little. So whatever we are observing is mostly because of the NV center. Okay, so this is actually up to this point we will like to show, and this is the ODMR signal that Professor Rock showed. So this we captured in the setup, and you can see we have the excited state ODMR at about 1.4 gigahertz, the left peak, the small amplitude dip, and on the right we see the main 2.88 gigahertz ODMR signal, right? And there is also some splitting of about 30 megahertz, which is because of the residual stress, because how they make these nanoparticles are that they grow the diamond and then they crush it in the milling. So some stress is left behind, and that actually splits the ODMR line. These are of course supplementary measurements of ODMR at different excitation power. So the idea is that we vary all the parameters and try to make sure that the observation we are doing is consistent and is coming from the sample of interest, not from any other background. And all the pattern in the experiment, that trends, etc., they follow our expectations about the behavior of the sample, right? So that is the idea of varying different parameters and cross-checking and so on. Okay, so now I will request Priya to demonstrate you the experimental procedure. And in the end, of course, we can
Now you guys can come forward maybe. Yeah. To make sample, here we have a glass slide, and this is the solution of nano diamonds. We simply we simply take this solution and drop cast it on a glass slide, you can see. Okay. Then we let it to dry maybe for 3 to 4 hours. Yes, and we already prepared the slide with a dry state, so you can come forward if you want to. So this is our fluorescence microscope setup, and as Professor Roque told that to excite NV we use green laser. So here we have a green laser which emits a wavelength of 532 nanometer. Then this light passes through a ND filter, which basically controls the intensity or power of the laser light which reaching at the sample. Then this we have a chopper which acts as a on off switch for the laser light. After that, this passes through a iris, and this we use to check the alignment of the laser beam. Then this passes through this periscope assembly, and it is used to increase the height of the beam. And after passing this periscope, we have another iris to check the alignment of the beam. After this iris, it reaches on this dichroic mirror. This is the dichroic mirror which reflects this green light towards this 40x objective, and this collects this light on the NV sample. This objective lens has a numerical aperture of 0.6. So basically it focuses on a very small spot on the sample, and the emitted fluorescence then travels back to the same objective and passes through this dichroic mirror and then falls on this notch filter. This is a notch filter, we can adjust it accordingly, and this blocks the 532 nanometer and allow to pass the fluorescence which is emitted by this sample, which is I will show you. So after that, this is a beam splitter, and it split the fluorescence light into two paths. One goes to the camera for imaging, and other one goes to this spectrometer probe. This collects the spectrum of this beam. So to show the spectra first, can we switch off the light for some time? You can see these are the nano diamonds. Okay, and yeah, okay, and this is the fluorescence light, you can see. Aage? This is the, okay, this is the fluorescence light, and if we want
There are patches in between. Are they easily
these
seen?
patches,
Yes.
these are the clusters of NB. So if we want to collect the spectra from here, then here we have a software of that spectrometer which we are using, and we simply on the take signal. So in this case, this is the spectra in a case where laser light and white light both are on. So now if we want to count only the fluorescence spectra, then we have to switch off the white light, and now we can collect the signal. So this is the fluorescence spectra of NV, and here we can see that here around 580 we have a bump, and which shows the NV0, and at 637 or 640 also we have a bump which is for NV minus for the sample.
Can you measure the power here? Did you show the
Yeah,
power?
yeah, I can measure. So, yeah. So why we use the white light at this place? White light is only used to see the NV. Otherwise, there is
So
no
what,
use of white light in fluorescence measurement. So, okay.
So what we will try to do, that we will try to measure the power of the excitation and the fluorescence
Yeah.
at different parts of the setup, right? So this is, can you describe what is this device?
This is a
The camera.
Achha. This is a power meter which works between 0.5, which can measure power between 0.5 milliwatt to 50 milliwatt. Okay. So
This is that is the maximum range, but it can measure up to nanowatts. So it is a
yeah,
very
and minimum.
sensitive power meter. Okay.
So if we measure
And
the,
you can directly read the power here, right? Yeah.
if we want to measure the input power, which comes from the laser, so here it is, sir.
So input power is about 70 milliwatt, which is a bit too much, right?
Okay.
So I think you can
And
maybe
after,
attenuate it. Okay, anyway, doesn't matter.
okay, after passing through this iris, it is, how much it is?
65 milliwatt.
Okay. And to, after that, if we want to measure after the dichroic mirror,
before the mirror.
dichroic mirror, okay.
Yeah.
So here it is.
So 59 milliwatt. So the power is reducing because every mirror is losing some power. Then how much it is entering in the objective?
Yeah, we can measure it from here. There is
13, 14 milliwatt power, right?
13
Entering in
milliwatt.
the objective.
Okay.
We don't want to measure, I mean, we can measure in principle, but let us say the worst case scenario, the objective absorbs 50%.
Yeah.
So it would be about 7 milliwatt going on to the
Sample. Yeah.
right?
Yeah.
Now, a part of it will be de-emitted. So how much is that, the fluorescence light?
Yeah. Okay. So I will show you. Yeah, it is.
0.2 microwatt. 0.2 microwatt.
Yeah.
So it is only 200 nanowatt power is emitted by the fluorescence, and then it is going into the spectrometer. So this is the reason that we need low light spectrometer and a cooled camera. So in that spectrometer, the camera chip is cooled to how much temperature?
Minus 80 degree.
Yeah, you can see here. Can
Yeah.
you show them, please? Yeah.
Yeah.
Minus 80 degree,
Minus 80 degree it
is
is
the cooled, so that the noise of the ECD detector, noise floor, is below is low, and then one can detect the low light. Right? So that is the idea.
And someone is asking me, can we see this fluorescence light by naked eye? So if anyone of you
Okay.
wants to check this.
And one more thing. So she
Yeah.
was saying we are claiming 200
nanowatt, yeah.
and then nobody is questioning the itna kam power. I mean, it's so low. So how are you sure about this?
Yeah.
So how can we make sure that this is 200 nanowatt? It's a correct measurement. Any ideas from you guys?
Removing the background.
Background, very good. So how much is the background of this?
So if we close the background
close the
light,
sensor.
you can see.
0.001 microwatt. So 1 nanowatt. We are measuring 200 nanowatt with a background of 1 nanowatt. So I think it's a reasonably correct measurement. Right?
Yeah.
Okay, what was the question?
If someone wants to see the fluorescence light, so you can check from here. Just put it here and you can see a red light on it between both of these.
थोड़ा इधर तो कैमरे में
Yeah.
we can all you will telecast live, right? You see the nice red fluorescence?
Yeah.
Because our eyes are very sensitive. They can measure even like few photons.
So it is coming in the visible region of spectrum.
Red fluorescence.
Red, yeah.
Red, orange.
You show the image, no? This one.
Hold it there. Zoom करने थोड़ा. और उधर देख करके स्माइल के साथ में. एक फोटो लेना.
अब तो लाइट ऑन कर सकते हैं भूपाल.
नहीं वो आएगा नहीं फ्लोरोसेंस.
ओके.
हमारी भी ले लो.
Happy faces.
Anybody wants to see? Come close. Yeah. जो पीछे हैं maybe they. Yeah.
Anybody
Please.
want to see the fluorescence spot
पहले
or the slide?
पहले गेस्ट को आपको बाद में आप तो यहीं हो रहे.
Yes, come.
Anybody from the back wants to? Okay. Then you can come here. Sure.
Yeah.
If guests are not interested, no issues.
Just put it here. You can see. You show the NV on the screen? No? No? Okay. To see the NV, you can see here. These all are NV. And these are the clusters of NV. This will give a good fluorescence because many NVs are collected here.
Laser is on the cluster of
No. We can get here also, but because the fluorescence signal is very low, that's why we put it on. What?
So by NVU means the vacancies?
Yeah, nitrogen vacancy center.
So what is the resolution of this camera that we can see the nitrogen vacancy clusters? Because nitrogen vacancy cluster will be on the nanometer scale, no?
Yeah, so this is also in the nanometer range, no?
No, but generally, I thought this is optical camera.
Yeah, this is थोड़ा what?
Grayish will not whitish.
What?
NV सेंटर कौन से हैं इसमें वाइट वाले जो बैकग्राउंड
ये NV सेंटर हैं, ये सब दिख रहे हैं ना?
जो थोड़ा ग्रे
हाँ ये सब NV हैं और ये जो स्पॉट हमको दिख रहे हैं ये क्लस्टर्स हैं कि बहुत सारे NV वहाँ पे कलेक्ट हो गए हैं और यहाँ पे भी आ जाती है फ्लोरोसेंस अगर हम सिंगल NV पे फोकस करना चाहें, बट क्योंकि सिग्नल कितना कम था, it is in nanowatt, that's why we focus it on a cluster and we can get a good emission spectra. Yes. You want to see, so I can move it. Okay. There. It can give fluorescence anywhere.
And if we focus on individual, then it will be very less output.
Yeah. Output is very low. That's why we take the signal on cluster. लोगों ने